that you guys will get this information. And when it comes to when we have our generator for the commercial building, for the industrial building, you're going to have at least two or three generators to back up the industrial building. Then you'll be required to size the feeders for these generators. Here's an example how to size the feeders for these generators. Here's an example how to size the feeders for these generators. Am I clear about this one, guys? Okay, so example number one. Here's what we have. It always starts with a diagram. I want you guys to understand what that diagram entitled. We have a switch gear, a panel basically, big switch gear. Inside it, there's a circuit breaker. It's called number 2. And we're bringing a cable and a conduit. The conduit is the blue, the cable is the black, number 3 and number 4. And to feed or to tie to a generator that we will size, that generator. And then in the generator, we have to ground the generator as separately derived system. They call it separately derived system, ground the generator. Bond the neutral to the ground. That's called bonding neutral to the ground for separately derived system. That's number 6. We have number 5 here is the grounding electrode conductor. It's called the grounding electrode conductor. And your job, my friends, is to size number 1 through number 6 for this generator system. One more time. We have a building. Here's my building. And I don't care what the circuit breaker here for this building. I really don't care what the circuit breaker size here for this building. What I care about is I size the generator using Cummins, right? Remember how we did Cummins software size generator? I came up with a size of 1344 kW. That's the size of the generator that I need. The voltage for the system is 382 220. This is more Europe type voltage, doesn't matter. The voltage really doesn't matter. 380 220, line to line, line to neutral, 3 phase. The power factor for this generator is 80%. Okay, that's what's given. I sized the gen using a software, came up with the size. Now I put my generator and I need to tie my generator to the switch gear in my building. How do you tie a gen to a switch gear? You have to have a conduit and a wire and a circuit breaker, right? So your job and mine will be to size the circuit breaker for this 1344 kW generator, number 1. Number 2, to size the cable, the feeder that takes the power from the generator to the switch gear. Number 3, the feeder has to be in a conduit, so we have to go size the conduit. Number 4, gentlemen, we need to size the conduit, right? Number 4. Number 1 is we talk about the generator here. Number 5 is we need to have the grounding electrode conductor. Every time we have a generator, Derek, you have to have a wire, take a wire and drive a ground rod and tie that generator frame to the ground rod. That's called grounding electrode conductor. Then with the grounding electrode conductor, the ground bar, there's a neutral bar here. You must bond the neutral to the ground if this generator is separately derived system. So we are bonding the neutral to the ground because we have decided to run this generator as separately derived system. Separately derived system, guys, you isolate the generator neutral from the utility neutral, and we're running this as a separately derived system. Any comments what we're supposed to size for this generator, guys? So we need to size the following. Number 1 is find the kW for this generator, the kVA. Here's a kW, find the kVA. Number 2, find the circuit breaker. Number 3, find the cable. Number 4, find the conduit. Number 5, find the grounding electrode conductor. Number 6, find the main bonding jumper or a system. It's called system bonding jumper. Any comments, any questions about what's needed for this generator? Does it make sense? Yes, no? Okay, everybody understand what we're supposed to do with this? Okay, let's go do it. So that's the first example that we're going to have. You guys have a picture of that one. Okay, the first thing you need to do when we size cables and conductors, we don't size them based on the kW. You have to size it based on the kVA. So you need to convert the kW, which is you are given here, the load, the kW. You need to convert this one into a kVA. How do we do this, Adam? We divide it by the power factor. So let's go ahead, let's use right here. So we take 100, 3, 4, 4, don't forget the K. Divide this baby by the power factor of 0.8. and that will get you a healthy 1680 kW. That's the kW. That's the 1680 kVA. I'm sorry, kVA, not kW. We already had the kVA. kVA. That's the kVA that you need for this building. The kVA that you need for this building. Let me go back. I think I mixed it up here. This is actually not the size of the generator. This is the size of the load that you need to take to a generator. That's the size of the load. Okay, and then to size the generator, guys, in kW, we're gonna go find divided by power factor. We find the kVA. Now, is this a standard size generator? We don't know. So we're gonna go. I gave you guys this sheet, so please look at that sheet. If you look under this, that one here, can you guys see that? Do you see where it says generator? I picked these one from Cummins. These sizes right here says gen. Start from 6.3 all the way to 3125. Can you guys see that? It says gen. Everybody can see them right here. Karen, does it make sense? Okay. So then the step number one is to find the size of this generator. I'm going to take the 1680 kVA. Take this one to DeWalt, and I put them in 3-13. That's the sheet that you guys are looking at. Okay? Do you guys see that sheet that you're looking at? Sheet that you're looking at. So Adam, if I have 1680 kW, based on that sheet, the next standard for this generator is 1875 kVA. That's the next generator size that I need, the 6th generator size, based on the load they have. Now, Derek, the good news is, typically, this number here, you get this number from the software, so you don't even really have to do that. This number here, right here, we get it from the software. You don't have to do this step. When you size, remember when we used Cummins, we came up with a KW, a power factor of 0.8. So you get this number from the software. That's a good news. Okay, now I want to go buy a generator, guys, with 1875 kVA. Any comments, any questions? Comments, questions? Any question why did we divide by 0.8? Because we always size things based on the kVA. Then you have to convert the kW to kVA, you divide it by 0.8. Power factor. Okay, so we know what size generator we need now. Now, moving forward, you're going to be using this value right here. That's the value that you're going to be using moving forward. You can't use this value or this value. That's your gen. It's bigger than your load, but you're going to go to the next standard up. So now we need to go size the overcaptation device. Everybody knows where number 2 is. I don't know if everybody knows that these are tied to the number here. So now I size the generator right here, number 1. This is my size generator. I need to go size the overcaptation device, then the conductor, then the conduit, then the ground electric conductor, then the main bonding jar. Cool? All right, let's go do it. Okay, in order to size the overcaptation device, Adam, you need to go find the current. So you use the 1875 kVA, divide this one by 1.73 times the voltage that I'm powering this one is 380. Remember, it's not 480. I'm using a 380 voltage system. You can use any voltage you want. The current, gentlemen, that you can come out of this is 2852 amps. That's my current. That's my current. That's my current. Okay. Now I need to size the overcaptation device. So the overcaptation device, guys, for my overcaptation device, I want to assume this load is going to be, the generator could be running fully continuous. So I'm going to go size my overcaptation device based on 1.25. 1.25. So I want to take the for overcaptation device, we're going to take the 2852. There is a section 440.13, guys. This section, NEC section, will tell you to size the conductor between the terminals of the generator and the circuit breaker. It can be sized at 115. At 115. So I'm going to take this one and multiply this by the magic number because I'm assuming it's continuous 1.25. I'm going to multiply this by 1.25, gentlemen.
What should it be, 1.25 or 1.15?
Okay, 1.15. Let's go. I think I have it here. Let me just go back a couple of steps here. Oh, I don't have it. I thought I did. Okay. The overcome detection device. If you look at, let's go there. Takes a second here to get it. Let me just go directly into that one. I thought I did have it. I think I know what happened. It's a good idea to go there anyway. Let's go to NEC code book. Okay. If you guys grab your code book, do you have your code book? Grab your code book, will you? Matt, you're gonna have a code book, right? Okay, so you guys cannot go through the program without having a code book. It's so we're going to go to generator. For the generator, here's the that article, the section that I did for you guys. This one, it says in order to size the conductors, you use the number 115. But that 115, guys, is only for sizing the conductors. Here's my generator. Here's my gen terminal, all the way to the overcap detection device. That's the conductor that you size 115. Do you see what I mean? From the generator to the overcap detection device. That's inside the generator for the most part. Now from the generator here, this one, this is you're going to treat it, if it's continuous load, you're going to treat it as 1.25 times I full load current. This would be times I full load current. See what I mean? You see where the conductors from the terminals of the generator to the first circuit breaker, 115. From the circuit breaker down to the switch gear, which we have, that's all we have, 125. I used to size it as 115, but that's a proper way. Okay, so let's go capture that. Okay, so we got that one. Okay, so that's what I wanted to make sure. So that's where that 125. Let's go directly into this. We got that one, guys. Okay, so the ampacity to the conductors. That wasn't the right. It's not the right. There you go. Seriously, Chad. There you go. I'm trying to match that one. Was it? I think it was 100. And then we can go down to conductors. There you go. So click here, click capture. There you go. Delete this one. That's close enough for us. Okay, so just want to take that one and go full. So 125, if you multiply by 1, you see where the 115 versus 125, and that's also for the conductor. So you're going to end up with 356 amp. Then you're going to take the 356. There's a 0, Chad. 0 amp. 0 amp.
3565.
Yeah, 3565.
3565. 3565. They give my copy today 3565 amp. And this is 3565 amp. You're going to go, if you take it to 240.6, assuming frame size, frame size, if you guys go there, that'll get you a 400 amp. That's the frame size that you need. A 400 amp is that big circuit breaker that's sitting there. That big circuit breaker that's sitting in the back. Any comments, guys? Any questions? So we have 3,565 amps, get you 4,000 amp. So the circuit breaker, Adam, is going to be a 4,000 amp circuit breaker. Any comments, guys, about this? Comments, questions? Okay, so we went to this area just as a reference. Now let's go size the feeder. The feeder, the same thing like reference 445.13, guys, but really it doesn't apply here. We're assuming it's continuous load. So for the feeder, match overcurrent protection device. I can't emphasize that word, match overcurrent protection device. So what do you do? My overcurrent protection device is 4,000 amp. How do you size a conductor for a 4,000 amp? How do you guys size a conductor for a 4,000 amp? What do you do? You're going to parallel. So how many sets are we going to parallel? I decided single-handedly to parallel 11 sets. So if you divide this by 11, guys, you're going to end up 364 amps, 11 sets. And then if you take the 364 amps, you're going to take them to table 310.15B16 under 75-degree column. And if you guys go there, it's going to give you 11 sets of 3 conductors. Each one of them is 500 kcm. 500 kcm. So that's how many conductors you need to carry a 4,000 amp. 11 sets of 500. What's the installation? Assuming we're coming from outside, THHW. We're coming from outside. Any comments, guys? Any questions? Any comments? Any questions? So what happened to the neutral? What size neutral do I need? What size neutral do I need? For the neutral size, guys, neutral. Neutral size. For the neutral size, the neutral cannot be smaller than the system bonding jumper. But what I typically do is I do this derating for the neutral. The first 400 amp, leave them alone. From the 400 amp, 4,000 amp, not 400 Chad. From the 4,000 amp, which is circuit breaker, the first 200 leave them alone. Anything higher than 200, guys, anything higher than 200, which is 4,000 minus 200, cut these by 0.7. Cut it by 0.7. Then add them up. So when you do this math, and you add them up, you're going to end up with 200 and 2,860 amps. 2,860 amps. Any comments, guys? Any questions? The first 200, leave them alone. Higher than 200, cut them by 70%. That's the rating than neutral. 220 to 61, I believe. Then I have to, the last step, guys, is you need to take the 2860 divided by 11 sets. You're going to divide this one by 11 sets. Can I divide by 11? No, you already divided it by 11. You have to divide it by 11. So you do 260 amp. That's your amp. And then from here, gentlemen, the last step, and we're doing the neutral here. So the last step is to take the 260 amp, take it to table 310.15 B16 under 75-degree column, and this will get you 11 sets of one conductor, 300 kcm THHHW. This is the size of my neutral. Any comments, any questions? Any comments, guys, any questions? Size of my neutral. Any comments, gentlemen? No? So that's basically the size of your neutral for this generator. Why did I multiply the 200, guys? The code 220, your reference here is 220.61. 220.61 tells you the neutral. You can derate this one at 61 at 70%. Anything higher than 200, you can cut it by 70%. Okay, now when we size the generator for this project, Karen, and I ask you guys to find the overcapacity device and the conductors, do you know how to do it? We're going to do it the same way. Okay, so that's your conductor. Now we need to find a conduit. The second thing, guys, is a conduit. Here's how these conductors is 11 runs. Can you guys see these 11 sets? We need to have these 11 sets. The 11 sets, we need to size a conduit. The conduit that I want to pull is rigid metal conduit. How do you do that? You take the first three 500 kcm, and if you guys THHW, you need to take them to chapter number 9, table number 5, chapter 9, table 5, and then that will get you 3 times 0.7901. 7901. The cross-sectional area. I'll show you that one in a second. Then we also have one conductor, guys, for the neutral. Let's use it green for that one. One conductor for the neutral. Here's one conductor. That conductor was 300 kcm THHW. Same table. You're going to take it to the same table. We'll get you 1 times the cross-section area is 0.5281. 0.5281. Add them up. You end up with 2.9 square inch. 2.9 square inch. The last step, gentlemen, that you need to do is you take your 2.9 square inch, take it to chapter 9, table number 4, under rigid metal conduit, and that will get you 11 sets of, what's the conduit size again here? 11 sets of a 3-inch rigid metal conduit. Any comments, guys? Any questions? Any comments? Any questions? So let's go. Let me take you guys to chapter 9, table 8 in the NEC code book. A quick reminder: if you graduate from Dunwoody not knowing how to use chapter 8, table 9, you should ask me for a refund. You know, so it's oops. You need your code, like I said, guys. Everything that we do has the code. You have to have your code for all the stuff that we do. You can't do your stuff without the code. So if you go to chapter 9, if you grab your code, please, and go to chapter 9. There you go, chapter 9 all the way. Um, okay, so the first thing we need to go, guys, is chapter 9. We said you have to go to chapter 9, table 5. Okay, so here's chapter 9, table 5. Here's table 5. Can you see that? Chapter 9, table 5. The installation that I have, Adam, is THHW. So I need to go all the way to THHW, all the way to here you go, THH, where am I, THHW? Did I pass that? THH, must have passed it. Okay. I need to go to, here you go. Can you see where it says THHW, guys, right here? Here's the installation that I need. Everybody can see that? Installation THHW. Right at the top, guys, it says approximate diameter and the cross-sectional area. We need the cross-sectional area right in here. Let me see if I can capture that. There you go. So when you use this table, you need the cross-sectional area right here. You need the installation THHW right here. You need the size, which is 500 right here. So this is 1, 2, 3, 4, 5. So you go right here. 1, 2, 3, 4, 5. Is that the number that we came up there? 7.7901, right? You multiply this by 3. Anybody knows why we multiply by 3? We have 3 of them. That's the number that we get. So I'm going to go take a snapshot of this. Capture. Okay. Any comments, guys, how to use the cross-section area of a conductor? You're going to go to table 5, chapter 9, table 5. Look at the installation. Go to the size. Under the cross-sectional area, find the cross-section area and multiply it by their size. The second thing that we need to do, Adam, is, what was it, too? There was 350, right? The 350, can you guys see the 350 is here? That's the 1, 2, 3. 1, 2, 3 is right here, right? And then you're going to multiply this by what? 1. Why multiply by 1? Is it 0.5958? Is that the one that I came up with?
We did 300, not 350.
Oh, did I do 3? Okay, sorry. I did 300, not 350. So that's the one right above it. Okay. All right, so we're going to go to the 300, which is the second. 300 is right here, and multiply this one by 1. Then add them up. Any comments, guys? Any question? You have to learn how to size a conduit, guys. Must. You know. Any comments? Any questions? Quick review of sizing conduits. You find the cross-section area. Now, when we added them up, Adam, we added these up. We came up with what was it? We came up with 2.9. So we came up with 2.9 square inch. That's the value that you need. Okay, so let's go take a snapshot of that and then go to the next table. Any comments, guys? Any questions? Find the cross-sectional area, add them up, which is this times 1, this times 3, add them up, 2.9. Now we need to go to table, which table now? We're going to go to table number 4. Now let's go to table number 4. Table number 4, guys, but which one of them? Rigid metal conduit. So all the way to rigid metal conduit. Rigid metal conduit, right here. Right here, everybody can see that? Rigid metal conduit. So let's erase this stuff here. So we need rigid metal conduit. So first you need, because Chad wants rigid metal conduit. Okay, and we need, so the number of conductors are over 2. So you fill 40%, right? That's your default. Over 2, you go 40%. Then Adam, if you're in Europe, you use millimeter, squared millimeters. We're in America, so we use inches, right? And what was it, 2.9? So I'm looking at, okay, here's 1.9 and 3. So I do have to go to 3 because I don't have 2.9. That will cross-reference me with what size? Was it number 3 that we came up with?
Yeah.
Number 3. Size 3. Yep, size 3. Any comments, guys? Any questions? Any comments? Any questions? Makes sense, Karen? Okay, so we know how to size a conduit. Now comes, guys, when we do for project, you come and you do a red line with your friend Chad. If I find a conduit that's not right, That's what we torture you with these lectures so you can take this information and build it into your project. This is your last chance of getting it, basically. So then we go close that one. Okay, so that's what I wanted to show you. So we talked about this. We got these guys, the cross-sectional area. Okay, let me see. So we got these for the cross-sectional area, and we got these, and we got this. Okay, so any comments, guys? Any questions before I go back to the size of the conduit? I know I spent a lot of time on it. This is not the first time we did sizing conduit, but hopefully there will be a review. So you're going to have 11 conduits of 3-inch rigid. Each one of these conduits is going to have 3 conductors 500 for the phases and 1 conductor 300 for the neutral. Done. Any comments, any questions? Yes, no? Good? Okay, so go there. All right, let's go size something called grounding electrode conductor, guys. Every power system have to, when you have a generator, it's like any other power system, Adam, you have to have a grounding electrode conductor for it. The grounding electrode conductor is sized based on table 250.66, okay? Table 250.66. So let's go to the grounding electrode conductor. Let's go to table 250.66, gentlemen, in NEC code book. So please grab your NEC code book and go to table 250.66. Okay, so 250. I'm going to start right here. All right, here's article 250 all the way to 250.66, which is changing soon. Here you go. Here's the table that you want. When you size a grounding electrode conductor, guys, you're going to be looking at this table. This table, grounding electrode conductor, that's the one that you take, Derek, and you tie it to the frame of the generator that's sitting outside. From one side, from the other side, go to the ground rod or the steel, concrete steel, concrete encased electrodes, all the grounding electrode system, which will be coming soon. Okay, how do you use this table? This table, guys, we use it based on the largest service entrance conductors or feeder. If you parallel, you have to multiply the number of runs by the size of the conductor. Okay, so let's go ahead and do the paralleling, and then we'll come back and check this table. So I want to go directly here. So how many runs did I run, Adam? I have 11 runs. So when we do this, the way we do them, you take step number 1, you're going to take a 500 kcm, multiply this one by 11, because I have 11 sets, that will give you 5500 kcm. Okay? Then you're going to take this 5500 kcm, you're going to take it to table 250.66, and you're going to get one conductor, and the size is 3/0 AWG bare conductor or covered or insulated. It really doesn't matter. Bare, covered, or insulated. So where did I come up with this number, Matt, my friend? You're going to go to the NEC code book, and if you guys look, I came up with 5,500. 5,500, it will tell you over this value, copper, because we're vested in a copper value, your number does not need to go more than 3/0. No matter what you do, you don't have to go more than 3/0. Does that make sense? So that's where I came up with this number. Any comments, guys? Any questions? Any comments? Any questions? How to use this table? Any comments? Any questions? Cool. All right, so we got our grounding electrode conductor. Now we need to go find, okay, we got our grounding electrode conductor. We need to go find the system bonding jumper. Now what the heck is a system bonding jumper? When you have a generator that running separately drive system, Adam, there's 3 phase and a neutral. You take the neutral and tie it to the ground with a wire. That ground wire that we just sized, that 3/0, you take a wire from the neutral and you tie it to the wire that goes to the ground. That wire is called system bonding jumper. You ground the neutral. We call it grounding the neutral. We, in a couple of weeks, guys, I'm gonna go over a whole lot of bonding and grounding. So for the time being, this is called system bonding jumper. For your system bonding jumper, your section is going to be 250 NEC codebook dot 28C1 and 250 dot 30 A1. These are all the references, so who cares? This is just to tell you that here's how we do it. You take the 500, exactly the same that we did, KCM, multiply it by 11, that will get you 5,500 KCM. Step number 1. Then you you ask yourself, 5,500 KCM, is it more than 1,100? 1,100 KCM? Is it more than 1,100 KCM? If your answer to this question is yes, right? More than 1,100 KCM, then, gentlemen, you're going to take the 5,500 KCM and multiply it by 12.5%, 12.5%. 12.5%. And that would be, if you do the math on that one, that would be 687.5 KCM. Okay? Because my answer is yes. Then, the last step that you need to do is take the 687.5 KCM. You need to take it, guys, to chapter number 9, table number 8. And if you go there, you need one conductor, 700 KCM. One conductor, 700 KCM. Any comments, guys? Any questions? Any comments? Any questions? You need one conductor, 700 KCM. One conductor, 700 KCM. Any comments? Any questions? One conductor, 700 KCM. Any comments? Any questions? Why do I multiply it by 1100 KCM, guys? Because these sections in the DC code book, it will tell me to do exactly what this meant. And we did it in the commercial project too, when we pedal. That's my main bonding jumper. My main bonding jumper is 700 KCM. Or system bonding jumper. Any comments? Any questions? Comments? Questions? Now, I will take you guys to Chapter 9, table 8. So if you go to Chapter 9, please grab your code and go to Chapter 9. Chapter 9, Table 8. If you go all the way to Table 8. Oops, here you go. Chapter 9, Table 8. So, Adam, here's my Chapter 9, Table 8, guys. You're going to go to the size that I came up with. So, I need to find the standard size. You go to the area, and you go to, of course, the circular mill. So, I was sitting at 600 something, right? Wasn't I? I was sitting at 687.5. So, keep going here. I need 600. We need to go a little bit down here. That makes sense. There you go. Keep going all the way, and you're gonna find that for 600, you after 200, after 211,000 here. Can you guys see that? You flip into KCM. So your next standard would be. Can you guys see that? Here's my next standard. My next standard would be 700 KCM. Everybody understand how to use this table?
The 687, you said down or you said up?
You size up.
That would be 750 because that's 355.
Well, wait a minute. We came up with our size was 687.5. You go up to 700. We were 687.5. We were 687.5. Yeah, you go to next standard, and the next standard. Oh yeah, I should have put the KCM here. The next standard is right here. 700 KCM. Any comments, guys? Any questions? Any comments? Any questions? So all this information, guys, will be in the first test that we do. So when you come, you're going to go to the NEC code book, go to these tables, and size them. Let's take a snapshot of it. Okay. So we got that. We got the sizes. And why did we multiply by 12.5%? These section will tell with 12.5% all the time. If your answer to this question is yes, if you are less than 11 kcm, where do you go? Table 250.66. 250.66. Okay. That's basically it for the generator. Your generator math will be identical to this generator. So you have to go find the overcome protection device, the conductors, and all these systems. Any comments, guys? Any questions? Any comments? Any questions? Do you need 5 minutes break before we jump into the busways? Or shall we jump into the busways? 5? Okay. I have 2 examples about busways, and then that will be it. Okay, let's go ahead, guys, into the busway system. Okay. The project that we have, guys, Adam is going to have 2 busway systems. It's going to have one is 208, 120. The other one is 480, 277. I showed you guys the book that we have has busway system. So the coming 2 exercises will be how do you walk you through sizing busway for a project. You guys are going to be sizing the busway for this project that you're working on, our project. So we're going to touch busways 3 times there. One time we're going to do these 2 exercises, how to size them. Not tomorrow, Friday, because tomorrow we'll have a field trip. Friday I'll go over 3 chapters that talk about busways. And also in the project that you guys are doing, not this week, not next week, the week after, you will be laying out busways in the manufacturing floor for this building. So we're going to hit it 3 times. You get it now, you're done. Okay, so busway sizing. If you guys remember the project that we have 2 busways, like I said, 128, 480, and you are to size the busway in the whole building. We're coming to this. Before we reach the busway, Derek, I would like to take you through 2 examples. How do you size a busway? Now, what the heck is a busway? A busway, guys, is basically big copper, 3 phases of copper bars sandwiched together with plugs from every side. So if you can imagine a copper bar, phase A, phase B, phase C coming in here, they're all fully insulated, sandwiched together, and enclosed in some type of metallic to protect them. And from each side of the busway, you have a plug where you can tap into the power to feed your motors. That's what a busway is. They typically use them in manufacturing floor. It's an efficient way of distributing the power. That's it. That's why they use them in manufacturing. Imagine each one of these chairs, guys, in this room is a machine, and you need to feed these machines right here in this room. So you have 2 options. Option number 1, you come to the panel here, and you take a conduit and a wire from the panel to each and every one of these chairs, which is machines. Option one. What's wrong with this one? Way too much wires going all the way back. The better option is to take a big chunk of power, like 400 amp, in a busway, 6 inches by 6 inches, as long as you want it to go. Bring it up from the panel all over right to the top, and from there you have SO cord, which is with SO cord. We used to have an SO cord. An SO cord where you tab them, you tab these you plug it into the busway and you go directly to each and every one of these machines. That's the most efficient way of feeding machines in a manufacturing floor. Okay? Again, we're going to have a whole chapter show you that one. So imagine this is your busway. Each one of these green fuse disconnect has a fuse in it and a disconnect tied to an SO cord, a cord, not a wire and a conduit, a cord from the busway into the machine. So here's machine 1, machine 2, machine 3, 4, 5, 6, 7, 8, 9. Your job, Matt, would be how to size this busway. So you can order this busway for the electricians to install it. Okay, the example that I have, does that make sense what the busway is? The NE sequence book guys talk about the busways in Article 368. Talks about what busways are and exactly what I told you. They are either copper or aluminum bus bars, fully insulated, sandwiched together in a close proximity, and enclosed in a metallic to protect them, and have holes from both sides where it can reach into the buses and tap into them. Okay, so we always think of busways, guys, as a panel. It's like a panel, really, except it's instead of a panel sitting in the wall, it's a panel that's hanging up in the air and you're tabbing from it. Every time you tab, the plug-in. There's the feeders, slightly different, but the feeders that plug in, you have all these plug-in that you can plug into them. A plug-in means you can tab into it. It's like a receptacle, you plug in. Okay, and you take an SO cord, a cord, and you tie to the equipment. The example that I have for you guys have the following. We need to size a busway. The voltage system is 480-277 three-phase. Typically, almost all of them are three-phase. You know, the loads that I need to feed from this busway. By the way, when we size things, we always size based on the load, right? We size panels based on load, transformers based on load, because that's what we need to feed. The load that I need to feed in this manufacturing floor are the following, the loads. 5 motors, 600 horsepower, 3 motors, 750, and 1 motor, 200 horsepower. You understand how many for a total of 9 motors. I have 9 motors that I need to feed from this busway. 4 and 5, 9 motors. Cool? Everybody's okay with this? So I brought a plug-in section, plug all these motors into it. Then to feed this busway, guys, there are 2 ways. Either you take the busway directly and feed it from the panel, or you bring a conduit and a wire, which that's what we're doing. We're bringing a conduit, that black one, and a wire, the red, and we're feeding this busway. Right? So you put the busway right here. At the end of the busway, you have a junction box, and you bring a conduit to the junction box, and you take it all the way to the panel, and you tie it to the panel. So that's what we're having here. We're having, so the first thing I need to do is I need to size the busway, number 1. What size busway? Number 2, I need to size the overconduction device that protect the busway. Number 3, I need to size the conductors, if any, you don't have to, the conductors, if any, that can bring the power from the panel, the main panel, into the busway. That's number 3. Number 4 is the conduit that's going to house these conductors. And number 5, gentlemen, is, I believe number 5 was the, I think it's, the equipment grounding conductor. Number 5 is the equipment grounding conductor. The equipment grounding conductor that ground this busway. Shall we go ahead and start sizing it? Any comments, guys? Any questions about what we're doing? So here's my main panel. I took a big chunk of power to feed a busway that feed a manufacturing floor. And that busway can be directly connected to the panel. That's one way. Or it can stop right here, it come from here all the way up and feed all these loads. At the end of it, you'll have a big junction box. You bring a conduit to it and feed it from the main panel. That's what we typically busways do. Plug-in busways, guys, don't go to the way all the way to the panels. If you look at them right here, here's all the plug-in busways. Can you guys see them? All these machines are plugged into them. They typically go where the machines are located, and then you feed them either through another busway that's called feeder busway, like in this project, or through a conduit to the line. Okay, so everybody understand we have 9, excuse me, we have 9 motors that we need to size this. Let's go do it. Okay, so now remember, we need to size the first the busway, second the overcome protection device, third the conductors feeding the busway, the conduit, as well as the equipment ground conductor. Now do me a favor. The standard busway sizes, do you see that sheet that I gave you guys? Grab that sheet from the wall and do me a favor. Go to page, the second page, which is this one. Do you see where it says busway or bus duct? Can you guys see that? So Karen, the way they size them in 3 phases, they go 225, obviously 225 all the way to 5,000 amp. Everybody can see that? You guys see it on that sheet? Okay, good. So let's go size. All right. So the first thing we need to go guys is size these conductors. So we have 5 motors. Each one of them is 60 horsepower. 60 horsepower from table 430.250, and the voltage is 480. You're going to find the full load current of this motor. There is a 3 of them. Multiply it by the full load current of these. Where am I here, Chad? I'm right in here. Okay, there you go. 385. That's what I thought. Okay, so the full load current for each of these motors, guys, is 77 amps. How many of them do I have, Adam? I have 5 of them. So you multiply it by 5. Okay. Then the 75. The full load amp is 96 amps. You multiply it by how many of them do you have? 3 of them. The third one, now Karen, which one of these is the largest motor? We have 60, 75, and 200. Which one of them? The 200, right? Is the 200 bigger than 75? I hope so. Otherwise, we might have to go to do different math. So the 200 is the largest motor. We're going to go to 240 and multiply this one by 1.25. Why do I multiply this one by 1.25, guys? The largest motor, you always add 25% to it. The largest motor, you always add 25% to the largest motor, right? Remember how when we did the calculation? 25% on the largest motor. Okay, so where did we get these numbers, guys? Let me go to the NEC code book, please. Grab the NEC code book and let's go to Article 430. Okay, so let's go to Article 464. Way at the end of Article 430, we have been here, guys. Here's a table that you need to find. So this is the table that we highlighted, right? No, not this one. Here you go, up a little bit. There you go, this table. And I'm going to go down a little bit so I can get directly into where the sizes that I need. Here you go. So we're going to do this one time, guys. Here's the table that we need, right? Can you guys see that? The voltage that I have is 480. Here's my voltage 480, which goes with 460. Derek, what was the sizes of the sizes? We have 60, 75, 200. I have 60, 75, and 200. That will correlate to 77, is that 96? And the 200 is 240. Any comments, guys? Any questions how to find the full load current of a motor from these tables? This is not the first time we saw that one. We've done it in the commercial project. So you're going to go find the full load current from here. Then you're going to multiply each one of them by their number, which you're going to multiply each one of them by their number. So this is the 60 will be multiplied, this will multiply by 5, this will be multiplied by 3, and this will be multiplied by 1.25. And Adam, the reason why we multiplied the 200 by 1.25 because it's the largest motor. We increased it 25%. Any comments, any questions when we came up with these amps? Man, does it make sense? Okay, so we're gonna go grab these, capture it. So that's my we got these numbers from. Okay, so now the rest is piece of cake, guys. After you do that, now add them up, add all these up, add them up, and when you do that, you will end up with 973 amps. 973 amps. Then you're going to take 973 amps, take it to the wall 3-13, guys. What's the next standard panel that you're going to have? How much? 973 amps. 1,000. Shut it a little bit. That's all right. 1,000. So the bus duct that we need for this system is a 1,000. You guys will do the same thing for the project that we have. Our project that we have is going to have the same sizing. You take the largest motor, add it to a 25. So now I know what size bus duct do I need. Now, if you have a future expansion, Adam, you just add a future expansion 10%. So you take this number. If you want to expand like 10% future expansion, multiply it by 1.1. All right, we got the size of the panel of the bus duct, and we know how to find where we found these amps. All right, overcome protection device. Let's go size the overcome protection device for that bus duct. So the overcome protection device, gentlemen, overcome protection device for bus duct, you're going to take the 973 amps that you came up with and take it directly to 240.6, and the next standard would be what? 100 amp. Everybody knows how to go to 240.6. Next standard will be 1,000 amp, not 100 amp, 1,000 amp. 1,000 amp. Busway feeder phase. So you go, if it's not a standard, Derek, where do you go? Up. See, we went from 973 to the next standard, which is non-adjustable 1,000. Okay, let's go to the feeder. Remember, the plug-in busway arm is coming up, stopped right here, and then I'm going to put a junction box, a pull box, or junction box here, and feed it with a conduit all the way to the switch here. Why would they do something like this, guys? Cheaper. It's cheaper to have the plug-in busway only where the machines are located, right? If you're feeding all these machines, guys, from the first floor, we're in the third floor. If you're feeding it from the first floor, does it pay to bring the power plug-in busway all the way to the first floor? No, it's a lot of waste of money. So what do? You have the plug-in busway here in this room, and then at the end you have a junction box, conduit and wire, take it all the way to the first floor. Or something called feeder busway. You can have a feeder busway, not plug-in. The difference between feeder busway and plug-in busways, plug-in busway has holes where you can plug into them. A feeder does not. You just take the power from point A to point B. That's it. There's no plug-ins in between. Okay, busway feeder, 3-phase. So let's go to the busway. So the way we do that one, guys, is match overcurrent protection device. You match the overcurrent protection device. Okay, I have 1,000 amp divided by 3. That will give me 333 amps. Everybody knows why I did that. So that's the parallel. Then you take your 333 amps, take it to table 310.15 B16 under 75-degree column, and this will give me 3 sets of how many conductors? 3 conductors. Each one of these babies is 400 kcm, THHN. Why THHN? We assume it's in the dry location. That's the size of the feeder that's going to feed this busway. Neutral. Now, typically busways, Derek, they don't have a neutral. A lot of busways, guys, don't need a neutral. They're really why? Because everything's three-phase. If you have to have a neutral, typically they don't have a neutral, so you just don't have a neutral. So we just take 3 wires to it. Make sense? 3 wires. Now, if you need a neutral, here's what you do for the neutral. The same magic number that we said, you take your, for my busways, since we have no overcomputation device, where was I? So we came up with, I start with then for the neutral, guys, you start with 1000 amp that we size the phases for. So the first 200 amp, leave them alone. Anything higher than 200 amp, what do you do with them? Times by what? Times 0.7, then add them up. When you add these up, guys, add them up, you're going to end up with 760 amps. That's my neutral size. Okay. Then you take your 760 amps divided by 3. Why? Because we already parallel 3. That will get you 253 amps. 253 amps. I'm running out of room to write here. So what am I going to do then? I'm going to go move these one here. A little bit, give me some room. I want to say these are phases for the feeders. I want to go give myself some room here, guys. And oops, right in here. Cool. Right in here. So the last step is you take the 253 amps, take it to table 310.15 B16 75-degree column. That will get you 3 sets of 250. 250 kcm. 250 kcm. Right here. What type of insulation? I'm sorry?
3 sets of 1.
Yeah, thank you. 3 sets of 1. Yeah. Yeah, 3 sets of how many? 3 sets of 1. Okay, so the neutral will be 250, gentlemen and ladies, and the phases will be 400 kcm. Any comments, guys? Any questions? Now, Karen, 99% of the time, you do not need a neutral for busways. Why? Because almost all the machines are 3-phase and they don't need a neutral. Do you guys know why they don't have a neutral for them? It's easier. Why do you need to carry another conductor? You can burn them at 3-phase delta or Y and they don't have a neutral. Okay, so that's any question guys about sizing the feeder and the overcomputation device? Okay, so let's go size, gentlemen. We're going to go size the conduit. Now for the conduit, I'm not going to go to the tables. You guys know how to go to tables by now, I hope. We're going to go to, here's what, we're going to do the calculation and you guys will verify it. I have 3 conductors, remember, so we have feeders, okay, 3 conductors, number 400 kcm. If you guys THHN, you take this one to table number 4, chapter number 9. We were there. Then you're going to end up with 0.58, 6 times 3. Remember, why do we have a 3? That's the first step. The second one is 1 conductor, number 250 kcm, THHN, same table. That will get you the size of 0.397 times 1. Add them up. You end up with 2.155 square inch. Okay? Then the last thing, gentlemen, so these are the calculation. The last thing, you're going to take the 2.155 square inch, take it to table number, which one is that? That would be table number 4, chapter number 9. I'm going to use EMT. I'm using EMT because I have to tell you guys what type of conduit I need. I'm going to use EMT. Could I use rigid? Yeah. If you guys go to the EMT conduit, you're going to end up, how many conduits? 3, and the size is 2.5 inch. 3 conduits, 2.5. 3 conduits, 2.5. So, gentlemen, you're going to have, that's basically what you're going to have. So here's my 250 kcm. The size for the phases will be a 400 kcm. These are my kcms. Now, if we're to pull an equipment ground conductor, Karen, then you have to resize. Later on, I'm going to pull an equipment ground conductor right here. If there's an equipment conductor, you put the equipment ground conductor right here and resize the conduit. Okay? Any comments, guys? Any questions about sizing the conduit? Everything that we're going to do from moving forward, we're going to get wire and conduit size and overcome protection device. Let's go to the next one, gentlemen and ladies. Where am I here? So here's my 3 conduits. Equipment grounding conductor, number 5. Can you guys see the word if needed? If you have an EMT conduit, Matt, here's an EMT conduit. See that conduit coming up there? If you have a conduit like this one, you do not need an equipment grounding conductor. A lot of engineers do though. So they like for reliability, for a better equipment grounding system, guys, they pull a conductor. If you have to size the equipment grounding conductor, again, can you see the word if needed? If needed, the equipment ground conductor, how do you size that basically? How do you size that? You go by overcurrent protection device for the whole system is 1,000 amp. You take the 1,000 amp, take it to table 250.122, and that will get you 3 conductors because we have 3 conduits. Each one of them is 2-aught AWG bare or covered or insulated. It really. Now, if you guys pull an equipment ground conductor, what do you need to do this? You have to go back. If you pull an equipment ground conductor, you have to go back and resize the conduit. Because that wasn't, I didn't size the conduit based on an equipment ground conductor. Does that make sense? Feel free to go do that one, but if you pull an equipment ground conductor inside each conduit will have the same size. Since we haven't been there, guys, let me go to 250.122, will ya? Just go to 250.122. Go to the NDC code book, 250.122, please. 250.12 and 2. Where am I here, Chad? Closer to the end. Should be closer to the end of here. 250. There you go. Here's the table that we go to find the equipment ground conductor, gentlemen. And you're gonna get sick of Chad talking about equipment ground conductor later on too. Okay, here's my table. It goes by the overcome protection device, guys. So my overcome protection device is 1,000 amp. I'm always listed in a copper company unless it tells you it's aluminum. So my size will be what? 2-aught. Everybody can see where we got this information, guys? Why did we go to this table? Because equipment grounding conductor are sized based on 250.122. Grounding electrode conductor are sized based on 250.66. When are you, Chad, going to go over all this? In 2 weeks. You get sick of the difference between all these grounding conductor. I have a sheet that I give you guys that has every definition of every grounding and bonding conductor that you can ever imagine. Okay, so let me take a snapshot of that. Okay. What? Snapshot of that. Snapshot. There you go. Okay, so let's go. So we got that one, gentlemen. Any comments, guys? Any questions about this before I move on to the next example? Comments, questions? Okay, got that. Let's go to another example, then we're done. Here's another example. We're gonna do the same thing. The only difference this time, Adam, is the voltage is 28120. I have a bus dot 28120. I have, how many machines do we have? See next page for loads. Let's see the next page for load. I thought next page for load. Here's the load that I have. I have 10 motors, 10 horsepower each, 7 motors, 15 horsepower motor, 3 motors, 40 horsepower, 4 motors, 7.5, and 2 motors, 5 horsepower. Tons of machines fit from this bus dock. Your job is to go size this busway. Cool? The same way, guys, busway, it's going to look something like this, phases and neutrals, and you plug them in. The first thing you need to do is size the actual bus duct. Then we need to go size the overcap protection device. Can you guys see that? Then we need to size the conductors and the conduits and the equipment ground conductor. Exactly, and they're all coming from a panel. The voltage is 28120, and we're basically repeating what we've done at the different voltages. Cool? Shall we do it? Okay. The first thing you need to do, guys, I'm not going to go back to table 430.250. You guys now experts in that table. If you guys go to table 430.250, make sure you go under 208 volt system. That's the key point. All of them are 208, okay? So if you go there, you're going to find the full load amp for this baby is 30.8 and multiply it by 10. Why did I multiply by 10, gentlemen? Derek, we have the amps multiplied by 10 because how many machines do I have this time? 10. Piece of cake. The 15 horsepower. The 15 horsepower, gentlemen, is 46.2 multiplied by how many? 7. The 40 horsepower. Now, here's that issue. Which one of them is the largest motor among all of these? The 40, right? So here's what you do because this is the largest motor. You take the first one, multiply it by 1.25 times, okay, let's do this one this way. The first thing you need to do is you take the 114 times 1.25 plus 114 times 2. Did you guys hear me? You take one motor, which is the largest. You take one motor, which is the largest, add 25% of it, and the other two multiplying. You can split the 3. I know this is confusing you. There is a 3 of these motors, right? One of them will be considered the largest, right? So you take the largest, multiply it by 1.25, increase it 25%, then add the other 2 to it. So 114 times 2, 114. So that's basically your 114. Okay? 114. Any comments, guys, while we took one of them, Adam, out of the 3, assume it's the largest motor and multiply by 1.25. Okay, now the rest is piece of cake. I have 24.2, multiply this baby by 4. And this baby is 16.7, multiply that baby by 2. Gentlemen, add them all up. Do not forget that you have to add them all up. Add them all up, and you're going to end up with 1132 amps. 1132 amps. 1132 amps. I assume you're going to verify that I did it right. Any comments, guys? Any questions? Find the amps, add them up. Then add on piece of cake. The rest, so that's the size. The first thing you need to size is the busway. Then you're going to take the 1132, take it to the Walt, which is the book that you guys have, or the copy that you have, at 3-13. And gentlemen, you get yourself at 1200 amp. did something wrong. Did you multiply 125 and then add 114 times 2 to it? Anybody verify it? Did you get it? Oh, okay, that's what I thought. It has been tested by a lot of students before. Okay, the size of the panel is 1200 amp from the table that you guys have. Overcome protection device. So we're gonna go. We size the panel. We need to go size the overcome protection device. The overcome protection device, Adam, is piece of cake. You take the 1132 amp. Take this one, gentlemen, to 240.6, and the next standard, guess what? Is a 200 amp. So that's next standard up is 200 amp. So we matched basically the panel. Okay, feeder for the busway. Feeder for the busway match over current protection device. Did you guys hear me? Match the overcome protection device. Okay, perfect. So let's go ahead and take the 1200 amp divided by how many? I want to go run 4. I decided to parallel 4. That give me 300 amp. Take this one to table 310.15 B16 under 75 degree column. That will give me 3 sets. 3 sets of what? 3 sets of 3 conductors. Each one of these babies is 350 kcm. What's the insulation? THHN. My insulation is THHN. Neutral, if any. The neutral, if any, again, I can't emphasize the word if any. In neutral, if any, you take, the way we do it, guys, you take the 1200 amp, the first 200, leave them alone. You take the 1200 amp, subtract 200 from it, times 0.7, add them up. So this looks like 900 amp. Then you take your 900 amp, divide them by 4. That will give me 225 amp. Take these 225 amp, guys, all the way to table 310.15 B16, same table. That will give me 3 sets of 1 conductor. Each one of them is 4 aught AWG THHN. THHN. Can I emphasize the word if needed? THHN. So 4 aught, 3 sets of 1 conductor 4 aught, if needed. Gentlemen, can you emphasize the word if needed? Typically, we don't pull a neutral, which is unneeded. Why wouldn't you pull a neutral, guys? If all the loads are 3-phase, why do we need a neutral? It'll be a waste of money. Any comments, guys, before we go into number 4 and size the conduit, the equipment ground conductor in this case? The equipment ground conductor. Comments, questions? Derek, did we make any mistakes? Yet? All right. So number 4 here is the equipment ground conductor. The equipment ground conductor, guys, is number 4. We size it based on overcome protection device. So this is step 1. Step 2, we take the 1200 amp, take it to table 250.1, 2, and 2. And that will get you 4 conductors. Each one of these 4 conductors is 3 aught AWG. And you can use bare or covered or insulated or THHN. Any one of these, typically THHN. Here's your three conductors. Four conductors, three. Why four? One in every run. I have four conduits. I cut out four. You're going to have phase A, phase B, phase C, and a neutral and an equivalent arc conductor. The neutral and the equivalent arc conductor, guys, are optional. If you need the neutral, you pull one. Typically, you don't. And the equivalent arc conductor, if you want extra grounding, you pull one. Typically, you don't. Does that make sense? These two, in this case. Okay, let's go size the conduit. Now, Adam, I'm going to size the conduit based on 5 conductors inside the conduit, not 4. Three conductors for the 3-phase, 1 for the neutral, and the last one, gentlemen, is for the phase. Okay, so let's go size the conductor, shall we? I'm going to start with my phases. I have 3 conductors. Each one of these babies is 350, KCM, THHN. If you guys go to table, chapter 9, table 8, you're looking at the top, you'll end up with 0.5242 times, how many of them? 3. Then, that's, these are the phases. Now let's go to the neutral. I have one neutral. The size of that neutral is 4-aught, KCM, THHN, and 0.3237 times how many of them? 1. And the last thing that I have is I have a ground, one conductor ground, guys. The size of that conductor is 3-aught. Oh, what's KCM here, Chad? Are you losing it? These are AWG. AWG. This one is rewriting things. 4-aught AWG. Okay? Be consistent. And then you take this one, guys, and it will get you 0.2679 times this by 1. What do you do then? You add these up, add them all up, after you multiply them, and you will end up with 2.1642 square inch. And then, Karen, the last thing you need to do is you take your 2.1642, take this baby to chapter 9, table 5. What type of conduit I'm going to carry? Looks like we're carrying EMT, aren't we? EMT, EMT. And gentlemen, when you go there, you would end up with 4 conduits. Each one of these babies is 2.5 inch EMT. Done. Any comments, guys? Any questions? So we took 2 examples to size busways, guys. That's it. Adam, if I can give you 100 examples, all the same, guys, for any type of voltage. We took 2 guys to size the busways because it's new. We took 1 example to size the generator. So here's how your system is going to be. 4 conduits, each one of them is 2.5. Each conduit is going to have 5 conductors. 3 of them, 350, 1 4-aught, and 1 3-aught. The blue, the neutral, and the green, the ground, these 2 guys are optional if you need them. The red, the phases, you must. You have no option. You have to have phases in a busway. You rarely, in a plug-in busways, if ever you have a neutral and a plug-in busway. It defeats the purpose. Okay, the last thing, any comments, guys? Any questions, comments? The last thing is your homework, gentlemen and ladies. Here's your homework for the generator. Homework number 3. Remember, I gave you 2 homeworks for the transformers. I know you guys gave it to me. Please do not forget to give me the homeworks next week for the transformers. For the generator, Adam, homework is going to be generator sizing. The load that I have for you is 1533 kVA. I can't emphasize the word what? kVA. Do you need to divide it by 0.8 here, guys? You don't need to do anything for 0.8. It's already giving kVA. You don't have to do anything with 0.8. Remember, it's already given kVA. The voltage is 482.77. Conduit is PVC schedule 80. Find the 7 items as an example. Cool? I put the only difference, guys, I can't emphasize this one. This is kVA. So can you guys write your 7 note? Do I have to divide by 0.8? No. Okay, example number 4. Homework number 4, Karen, is busway system. The voltage is 28120. The loads are 3 motors 15 horsepower, 4 motors 20, 5 motors 250, 6 motors 50, not 250, 25, 6 motor 50. The conduit is EMT. The insulation is THHN. And you are to size all the items that we did for the busway. The 5 items that we did for the busways. Any comments, guys? Any questions? Comments, questions? So that will conclude our lecture for the day. Any comments, questions? Like I said, Derek, tomorrow we're going to do a field trip. Friday, I will spend, guys, 2 lectures about busways again. So we'll talk, but not calculation this time, how to install them and what's not. So the construction and what's not. Thank you.